So I would like to welcome everybody to our fourth session of the 2023-2024 Forest Climate Learning Exchange Series. I'm your host this week, Chad Papa. I'm a research assistant with the Forest Carbon and Climate Program, as well as a PhD candidate in the Department of Forestry. To start off, I'd like to now acknowledge and thank our co-hosts for this year's series, the Society of American Foresters, commonly known as SAF. SAF is the national and scientific and educational organization representing forestry and related natural resources professionals across the United States. Founded in 1900, SAF promotes science-based sustainable management and stewardship of the nation's public and private forests. So for today, our presentation is by Adam Daigneault and Daniel Hayes, both from the University of Maine. Together, they will present assessing alternative modeling frameworks for carbon accounting in managed forests. We sincerely are thankful to both Adam and Daniel for taking their time with us today. But before that, I'd like to briefly share a few housekeeping details. To automatically receive registration details and information regarding upcoming webinars, please join our mailing list by either scanning the QR code on the screen or by emailing us at forestc@msu.edu. A recording of this session, along with a copy of the slides and any supplemental resources, will be posted to the Learning Exchange Series webpage. This presentation will be followed by a Q&A session. You can either use the chat feature or the Q&A function at the bottom of the Zoom interface to submit your questions at any point during the presentation, and we'll do our best to address as many questions as possible as long as time permits. If you're calling in on the phone but can email, you can also send questions directly to forestc@msu.edu, and I'll drop a link for that email in the chat, as well as I will drop a link for folks to be able to sign directly up to the FCCP mailing list as well. And kind of lastly, with housekeeping, so attendees are qualified to receive CSE credits from SAF. The credits will be automatically applied if you register for the event with the email associated with your SAF account. And so with that, I will hand it over first to Daniel. Thank you so much for agreeing to share and present with us today.
Sure, thank you for the introduction. I'll share the screen here, which will stop your sharing. So thanks very much for having me on, and Adam as well. So as Chad said, that we will tag team this presentation. So I'll start first with some background information and kind of give a little overview of what we're talking about here with carbon budget modeling and accounting in forests, and then Adam will go in and talk about the assessment and sort of application side of modeling frameworks that we had discussed.
So Dan, before you go, we're seeing the
oh, you're kidding.
But the opposite.
Sorry. I see that now. Thank you. See, we practiced this and it didn't just do it this way. Let's try to share the PowerPoint directly, but that should work. Yep. Okay. Thank you. Okay, so since I'm starting and I'm a professor, we have to start with this slide. I don't think you should be allowed to talk about the carbon cycle without starting with this. So you've all seen it, but we need to remind ourselves of why we're talking about this sort of thing, noting that measuring the CO2 concentration in the atmosphere increasing dramatically since over the last several decades, and what it is that causing climate change, where a big interest to scientists and policymakers, of course, is where does this carbon that gets sent into the atmosphere through fossil fuel combustion and land use change, and where does it end up? And these are global carbon assessments where we do carbon budget accounting, essentially, which is what we're going to talk about here from the forestry perspective. But from the global perspective, we start the whole process by looking at where the carbon goes, and it turns out that of the emissions, gross emissions, only 50% of those approximately actually stay in the atmosphere. And so where does the rest of it go? It turns out that about half of that is into the ocean. You can see here in the darker blue line, it's a pretty steady uptake. And I don't like to make marine scientists upset with this, but it's pretty steady and it kind of predictable, and it goes along as it does, mostly by diffusion. Of course, there's biology in the ocean, but where things get really wacky, as you can see here, going up and down year to year, and it's difficult to figure out and to reconcile how much of that goes into the land, including forests. And the study that's getting old now, but was a very useful study to put together carbon budgets for the world's forests. And it turns out that if you add all these numbers up from various different countries and regions where they have inventories, which we'll talk about, and account for all these different processes, that the most of that carbon that we saw in the last slide going into the land, of all the ecosystems, most of it goes into the forest. And so that's where the largest sink of atmospheric carbon is globally, is in forest. So and that sink has maintained its strength over decades now. And so it really underscores the importance of the role that forests play in the global carbon cycle. And so as such, there's a lot of interest in what we call carbon MRV, monitoring, reporting, and verification systems. These are that keep track of carbon, basically, in forests and other ecosystems. And these are needed for international agreements like the United Nations Framework Convention, International Panel on Climate Change. So all of those numbers that go into the policymaking that happened in Dubai last November, and Egypt before that. There's also importance for this sort of thing for keeping track of efforts in REDD+ or other forest conservation programs, particularly in the tropics, as a way to not only mitigate climate change and global warming, but also to promote sort of the parallel goals in biodiversity and other conservation efforts. And then there's increasing interest in these at even the state level. In the United States, for example, here in Maine, we have a law of needing to reach certain climate goals at certain levels, including net emissions goals, which takes into account not only the fossil fuel emissions, but then how much the forests and other natural and working lands can take up, to kind of get us towards those net neutral goals that Maine and other states have set. And we'll talk a little bit more about that. And then, of course, there's the carbon trading markets and companies and forestry, in particular, managers that get into making decisions about whether to get into these trading markets and how to manage their forests for these benefits. So there's a lot of need for that. There's a proliferation of MRV systems or pieces of systems, components that are out there, efforts that are done from local scales to state level to globally. And so there's a bunch of icons just show those. And so we'll talk about some of this in terms of forest inventories, like in Canada and the US. And we've also worked on other remote sensing carbon monitoring. NASA has its own carbon monitoring system program, and been involved in the North American carbon program that brings together these efforts from Canada, US, and Mexico. And even showing here, we have now doing this at the state level to work on a state of Maine carbon budget. So just as an overview of the presentation, I will be talking about the sort of summary of what, or an overview of how, what these models are doing and how they work, what kinds of things we need to keep track of in terms of the different components of the budget, how we measure them, how they're modeled, and talk a little bit about just general types of models and their pros and cons. And then in part two, Adam will go into more details about how you decide which model to use for your particular application. So I'm going to start out with a fun little exercise of at least I think so. Hopefully you will too. Of what are the components of the carbon budget? So what is it that we're talking about here? And this might be review for some of you, but I think it's useful to go through and look at the different components in the budget and talk about how we keep track of them and measure and model where the carbon is going through our system. So I'm going to start with we're going to look at two things. We're going to look at pools of carbon and fluxes of carbon. So pools are those kind of containers, or buckets, as some people call them, of where the carbon goes, and then the fluxes are the how the carbon moves from one component to another, one bucket to another. So as foresters, we also start out thinking about above ground biomass. That's the one thing that we probably know pretty well and can measure pretty well. In inventories, we all know how to go out and set out plots and measure how much volume is in or at least measure the things that you need to know to figure out how much volume is in a plot, and then convert that to biomass. We also got to keep track of the below ground biomass. So that's a little trickier, of course, right? We can't necessarily remote sense that or measure it in the field. So need different equations, allometry particularly, to attach those roots on there in terms of how much carbon is there. So there's a couple pools. Of course, the soil, organic matter is another major pool of carbon that needs to keep track of. And again, it's harder to measure. You can't remote sense it, and it's hard to have, dig a bunch of soil pits to measure the carbon content. So there's various ways to model that. And of course, there's even a lot of strange people, like here at UMaine as an example of Sean Fravor, that actually go out and measure all those logs and sticks that fall on the ground and do litter traps, because that's another important and very dynamic pool of carbon that we need to track. So those are the main forest pools in the forest ecosystem. And now let's talk about some of the fluxes. And so here's where we think about where the carbon is coming into the system, and that is through primarily, well, at the beginning, it's through gross primary production, which is you might know as photosynthesis. And that takes in carbon from another pool, which we consider is the atmosphere pool. So the forests are drawing down carbon dioxide out of the atmosphere and fixing it through photosynthesis as living biomass. They also, as part of that process, have maintenance respiration that returns carbon back to the atmosphere, which is also a gigantic flux. So the small difference between two really large fluxes in GPP and respiration is net primary production of the actual growth. And then of that next annual growth is that carbon can be stored in the wood and leaves, of course, and roots of the trees, but also as those pieces of leaves fall and pieces of trees drop off and trees die altogether, they get added to the woody debris and litter pools, which is then incorporated into the soil as organic matter. That is then can be returned to the atmosphere. Some is stored in the soil, of course, and then some is returned to the atmosphere from the soil and the litter pools through heterotrophic respiration, excuse me. And we notice there another gas comes into play at this point, where most of our fluxes are CO2 now that come into the system through photosynthesis. Now we can release that carbon back to the atmosphere through respiration as both CO2 or methane, which is a much stronger greenhouse gas. And then adding another way for carbon to be returned to the atmosphere, of course, is through combustion. And so certain ecosystems, of course, this is a big factor in the carbon budget that needs to be tracked, is carbon can be combusted both from the live above ground, from the litter, from the soil, depending on the severity of the fire, and that can be released depending on fire behavior as CO2, methane, and carbon monoxide. So that's the sort of vertical fluxes from the ecosystem. But then there's this other component that's often overlooked, but is really critical for balancing these budgets. We found some of you have heard about a lot of these comparisons in carbon budgets from top down and bottom up, which we'll talk a little bit about. There used to be this thing we talk about called the missing sink, because we couldn't reconcile what the atmosphere was showing versus what we could measure on the ground. And so it turns out that there's a lot of this carbon that is moved laterally from the soil as whether erosion or leaching, particulate organic carbon or dissolved organic carbon, and that is moved laterally and goes out the river systems. And so it's not necessarily seen as a vertical flux back to the atmosphere. It's somewhere else as carbon moves from the ecosystem through the water aquatic system. And speaking of these of moving carbon laterally, another big component of that obviously is through harvesting. So carbon that's taken off the ecosystem site and moved to some other place in some other form. And this is in the form of HWP, or stands for harvested wood products. So we keep track of those in different pools, depending on their lifetimes. And so I have whether that's chips or paper or put into to boards and saw logs, and they're used for different purposes. We also need to keep track of this pool in terms of things that can go in and out of that pool from your sector or your geographic area in terms of imports and exports of wood. And that's another important component that moves carbon around. And then we keep track of the atmospheric fluxes from these pools as their different lifetimes, whether they're burned at the mill or they've got a little bit longer lifetime in paper or longer lifetime in building products or furniture and buildings and things like that. Of course, then those products that are in use can be moved to solid waste disposal if they're not recycled as in landfills. And then over that whole system from end use and landfills, wood products, we have burning and decay that can release carbon back to the atmosphere as carbon dioxide, methane, and carbon monoxide. And as part of that, where it gets also complicated, of course, is how much of that energy is offsetting as bioenergy from wood, and how do you account for that in the system, which Adam can talk more about, and I see in future webinars that's discussed more specifically. But that is another component of it. And of course, in the end, we're looking at the energy sector and the anthropogenic emissions of fossil fuels in general, from transportation, from commercial activities, things like that. In cement production, that's not necessarily specifically part of the forest sector per se, but we are often looking at those as a comparison, because we want to know about all of the fluxes of carbon and storage of carbon in the forest sector. How much does that offset these anthropogenic emissions? And that gets us back to these questions of being able to track the role of forest carbon in meeting climate mitigation goals. So that's a nice tour of the forest sector carbon budget. And basically, those are the components by which carbon is accounted for in these different pools and fluxes. And so from there, there's a bunch of other issues which just to be aware of is, how do you define the forest? What is a forest versus not? And there are IPCC international guidelines for how that's done, and it's often called the placed in this land use change and forestry categories. So LULUCF, that'll be when you see the reports from the IPCC globally, internationally, and also the U.S. Environmental Protection Agency, the reports that they release for the national and state level, they produce carbon estimates for all these different categories. And you can kind of see some of these over in the visual on the right, not only forest land, but agricultural, croplands, settlements, and other categories that sort of set up your system. And what is the boundary of that system? That's a question that you have to think about. And why I put the truck back on here is because is like where does that carbon get accounted for? Who gets credit or offset for carbon based on where it's produced versus where it's consumed and removed and released back to the atmosphere. So there's default approaches when you don't have much information, which is just a kind of a time one versus time two stock change that a lot of countries use to report their carbon budgets. There's also the preferred in the way the US and most countries do it as a production approach, which means you account for the carbon that you grow in your wood, even if it is exported and released back to the atmosphere somewhere else, you still account for it in your budget. And then I also mentioned here the atmospheric flow approach, which takes into account these different movements of carbon, both imports and exports, as well as the lateral fluxes that I mentioned through the aquatic system and in wetlands and coastal blue carbon. These are important more in research to figure out, can we reconcile what we're seeing in the atmosphere versus what we're measuring or modeling on the ground. And so that's an important activity to be able to understand what's happening with the carbon cycle and how we can effectively account and model this going forward. And I also mentioned here, geographic boundaries are important as well. In the case of what do you consider managed land? A lot of carbon incentive programs are based on the idea with forests that you can do certain management actions that can promote carbon sequestration versus situations where you have natural or unmanaged lands that are maybe burning up, in Canada, or they're releasing carbon to the atmosphere and they're not managed, and there's sort of nothing you can do about that. That carbon is still going into the atmosphere, so it's still important to track for purposes of mitigation and climate change. But there's not really management that you can do to kind of in some cases to kind of set your management policies towards. So just to be aware of that, the example here would be both in Canada and the US. In the US, for example, the FIA program does the forest inventories for all of the lower 48 states, but only partial of Alaska, where they have national forests and actual inventories. For the interior of Alaska, there is no formal inventory yet, and so that's not included in the carbon accounting for the United States, even though there is lots of carbon there and there's fires and other things like that. So something to be aware of as far how this accounting works. And so I want to just segueing into Adam's section part 2, we want to just talk generally about what the role of modeling is in forest carbon assessment. So models are obviously really important for both the process understanding and for the policy understanding and recommendations. And so we have a couple of bullet points here about just being able to understand carbon processes. So some of the things we talked about in terms of photosynthesis and respiration and harvesting impacts and that sort of stuff. And so we can put those ecological processes into models, either empirically or as numerically and process-based, which I'll mention. And this helps us understand how these processes may respond to future stressors like climate change and droughts, and actions that we can do in management like silviculture or other disturbance impacts, and see what those are into the future. So we have an example on the left here showing a model projection under different scenarios: normal, no harvest, different climate scenarios, and what different indicators of forest carbon would look like out into the future. And of course, these are important to run these scenarios for different policy evaluations, which Adam will talk more about. So quickly, just some real general back to school here, modeling 101, but often in carbon modeling, we talk about a lot of you are familiar with the statistical and empirical approaches that we use, sort of just showing some general visuals here of how you might calculate volume based on measurements of the DBH and height of an individual tree. And this is using a statistical approach, and then turning that volume measurement of a single tree into a volume measurement for a plot, which you can then do an estimate of plot biomass. And then if you come back at some inventory time later, 5 or 10 years later, and do the same thing, you can do the delta carbon and get your estimate of sequestration or loss of carbon in that particular forest plot from time 1 to time 2. Then there's also another approach that's based more on numerical simulation. So this is where some of us actually use calculus on a daily basis. And this is where we're actually simulating the process. So rather than just measuring carbon or estimating carbon at one time and subtracting it from a previous time, now we're actually looking at the processes to control the movement of carbon from one pool to another and between the ecosystem and the atmosphere. And this is often done with simulation models, which we'll mention here as part of the assessment as well. But these basically look at the fluxes of carbon more than the stocks, and so you can do things like estimate NEE, which is net ecosystem exchange, the actual vertical exchange of carbon dioxide between the forest and the atmosphere, and that's as a change in carbon over time, and you can model that out. So it's kind of two fundamentally different ways of looking at it. And then in terms of the modeling, I also need to talk about, you'll often hear differences between top-down versus bottom-up approaches. And so I want to mention this here as an important, not that we have time to go into a lot of the details on this, but from the top-down perspective, we have these constraints on the system measured from the atmospheric perspective, essentially. So that could be simple budget approaches. What's the carbon dioxide concentration on the west coast of the U.S., and then you go measure it on the east coast of the U.S. A day later or a week later, and you can assume that that certain amount of carbon was drawn down or released in between as the carbon air parcels moved across the continent. And so there's different ways of then modeling that closer down to a grid cell level, if you can do these Bayesian inverse models to figure out where the carbon fluxes are happening geographically over space based on the signal in the atmosphere. We also have more direct measures of CO2 flux measurement at idiocovariance towers, like an Ameriflux network, where there's towers in all these different ecosystems that are actually measuring the vertical exchange of CO2 with the atmosphere in the forest. Those are really great measurements, but they're limited in spatial coverage. So just these 1 kilometer tower footprints at certain spots. So those are a couple examples of the top-down approaches that we can use to help understand the system and constrain our estimates from the bottom up, which is what more of us are going to be likely to use for applications. And we'll talk about those more in terms of the inventories, bookkeeping, and ecosystem model approaches as general approaches to the modeling forest carbon. So a lot of you are familiar with the U.S. Forest Inventory Analysis Program that does the forest carbon accounting for and reporting for the United States. And so that's based on putting out a bunch of plots all over the place and measuring different things that you can then ultimately get a lot of estimates of different attributes, important attributes out of, including biomass and carbon. And this is based on that delta method, where you're going and measuring a plot at one time and then measuring it again, and you figure out what the sequestration or loss was for that plot. Another slightly different approach to an inventory is similar to what Canada does. And I should say that there's not a real clear separation here. There's a lot of mixing and matching with both programs, but generally we think of the U.S. approach as a stock change approach, whereas Canada uses a gain loss method, and that is based on measuring carbon at one point at plots, and then basically keeping track of the changes in carbon by looking at disturbances in management, having statistics on those things, and then you can kind of grow yield curves and disturbance succession relationships going forward to kind of track your carbon changes over time. And that kind of segues into this idea of bookkeeping models, which are used in a lot of countries, especially if they don't have formal inventories, which I'm showing Mexico now does, but at this time that this paper was published did not, and a lot of other tropical countries, especially developing nations, kind of use this more of approach where you have some general estimates of the carbon density of different forest and land cover types, and then you basically make a map of those and using remote sensing often, and then you can basically paint by numbers and say, okay, if this satellite remote sensing map tells me that this certain type of forest is here in this pixel, then I would assign this carbon to it, this carbon amount to it. And then what you need to do once you have that map at one point in time, then you need to kind of update it as you go. Also, a lot of times using remote sensing to update land use change and track disturbances that you can then keep track of or models very simply in a sort of spreadsheet format. The pools, the different pools of carbon to get your total estimates of carbon pools and how they've changed over time. So that's sort of a straightforward and more simplistic way of doing it. I do need to mention the role of remote sensing here, being a remote sensing professor myself, and working on a lot of NASA efforts to do carbon monitoring, reporting, verification. And this remote sensing is used in all these different modeling approaches, but shown here is sort of a bookkeeping approach where you do something similar, where you can use airborne LiDAR, for example, to pair it with plot measurements to estimate biomass instead of measuring trees, you estimate it from measuring point clouds, LiDAR point clouds, three-dimensional models of the forest structure, and then you can map that across the whole larger region, like is shown here on the left over New England, where we have airborne LiDAR. And then what you need to do is come through with something like a satellite record from the Landsat that goes back into the 1970s even, and you can track disturbances over time and update your carbon mapping with these remote sensing tools. And we move into a couple examples of mechanistic models where we're actually looking at processes, so a little bit more than just measuring and multiplying or keeping track of bulk changes. We are actually simulating processes in the forest, and many of you are familiar with these, what we would start with these forest gap models that are used at the plot and stand level to look at succession and resource competition among trees. And you can simulate biomass accumulation and loss that way for limited spatial extents. If we want to get a little bit larger, a broader scale in our spatial extents, you can use forest landscape models that simulate similar dynamics with spatially referenced data that can look at things over time, and we'll look at examples of that as well. And then more, I wouldn't say sophisticated, definitely more complicated, more complex and computationally intensive forest ecosystem models where you're actually modeling, simulating all of these different processes that are kind of represented in the graphic on the left. And I just want to mention a couple things that you may have heard of. We talk about these, there's different terminologies that all kind of refer to similar things, but we have forest ecosystem models that are also called sometimes terrestrial biosphere models, or land surface models that simulate all these different processes as a component of these larger climate or earth system models. And they're also even connected and coupled with economic models to look at, and socioeconomic models to look at these integrated assessments. And so different consequences of changes in economics and politics that would have on the carbon cycle. So these are numerical simulation of climate-driven ecological processes, as I've mentioned before. So these models will all have some sort of coupled plant, soil, water, energy cycles for not only carbon, but the things that affect the movement of carbon, like water and energy in the ecosystem itself. You can have, another terms you might hear is you can have prognostic models or diagnostic models. Prognostic models, they have their own internal prediction of LAI, leaf area index, or photosynthesis, and that's done through these enzyme kinetic EK equations of some type that actually look at stomatal conductance of CO2 moving in and out between the atmosphere and the vegetation. And so those can be used to predict carbon cycling into the future from an ecosystem perspective. We also have diagnostic simulation models, which are using light use efficiency equations that are based on remote sensing. So those are another class of being able to do these types of sort of how you simulate the carbon entering the ecosystem through photosynthesis. Those, of course, you don't have future remote sensing, so those are more of a diagnostic approach to look at what's happened over the satellite record versus being able to predict that into the future. Then there's also what we had called big leaf models. And so these are the older original forest ecosystem models that sort of just pretend that a grid cell on the planet was just this big one leaf that had carbon going up and down through photosynthesis and respiration. They've gotten more sophisticated and at representing more dynamic processes like dynamic vegetation models, DVMs, and now ecosystem demography models that you might have heard of, the ED model that actually simulates these processes as well as doing some of those gap dynamics and landscape type model approaches. So they're bringing all these different pieces together to be able to simulate forest ecosystems and carbon. So there's a really super fast view of the background of modeling, and I will turn it over to Adam to talk about the practical applications of selecting carbon model frameworks. Oh, Adam, you're muted.
Thank you. All right, so if you're like me, you kind of went, as Dan went through that presentation, said, wow, there's a lot of amazing things that are out there, but wow, this is equally confusing in terms of, look at all these different things that can be modeled. There's all these different pools and fluxes, a number of different models. And so the idea is, how do we figure out which one to use? And so as a result, we kind of came up with this carbon model selection framework, where it's particularly tied to models that can be used in the eastern half of the US. So Dan noted there's multiple models and frameworks available, and really the needs and the complexity about sort of what model you might need can really vary. So it depends on what carbon pools you're interested in, whether you're measuring stocks and or flows, what's the spatial and temporal scale you're looking to measure over. Are you looking to track changes in management, or are you okay with sort of a business as usual approach? Are you looking to cover those harvested wood products? Do you need to account for land use or land cover change? What about other disturbances like climate change, pest, disease, fire impacts? As you can see, sort of every single one of these components could drive sort of what that forest system could look like, and could have effects on what forest carbon could evolve as a result. So even with that, you might just step back and say, maybe I'm not at the stage where I want to be able or have the capability to do a complete sort of forest ecosystem type model. And so really at first, any of this modeling really need to think of is like, what forest model should be used to, say, generate yield curves? Because we need to even know what's on the landscape and how that might evolve, right? And so each region has a number of different sort of growth and yield studies and models that can be used, right? And so just an example, if you get more than a dozen just sort of growth and yield models, and the one that Dan showed an example of is through FBS, which is the National Forest Inventory Systems FIA sort of led one, right? But there's a number of other ones that we could potentially choose from, depending on, again, what questions you're trying to ask. Dan also alluded to the Canadian model, CFS CBM, right? There's increased application of that, including ones that have been utilized by Chad and others at Michigan State and their collaborators to answer similar questions. So that's another one that's sort of been sort of used more and more in more recent years. So the question we had is, well, there's more than a dozen models that we know of that have been utilized or could be utilized to model forest carbon dynamics in the eastern US. And so just a quick sort of Web of Science sort of search for these 15 carbon models that we feature in our assessment turned up 857 manuscripts that were written since 1990, right? And the most common models were CBM, CFS3, Day Center Century model, the Landis model, TEM, FBS, PNET, and the last one should say Woodstock instead of TEM, right? But what we're seeing is that a number of different models have been utilized, and in general, the trend is pretty stable or moving upwards for a number of these, right? So there's a lot of interest in sort of using these models and publishing the findings, but it doesn't really answer the question of, is there the best model to use, right? Because it's apparent that, at least in the literature, a number of these models are being used and then deemed to be good enough to have peer-reviewed publications. So as a result, we started with, as a sort of a team of experts, to just come up with a number of questions that ones might want to consider when selecting a forest carbon model. And all this is included in the report, of which I shared the link. But the things you want to think of, again, is sort of what carbon pools do you want the model to account for, at what spatial scale, right? Is it pixel, plot? Are we looking more at the state or national level? What time step do you need to estimate these carbon dynamics? How can the model incorporate policy relevant management alternatives or silvicultural systems, best management practices? Does it incorporate ecosystem disturbances at all? And do you want to cover that? How do you account for harvested wood products, or does it just stop at the sort of forest ecosystem level? What do you need to do in terms of model parameterization, and what data is available to do that? Not all models are available such that they're already parameterized for your region right off the shelf. Often you need to go out and collect your own data or parameterize it. How sensitive is the model to these sort of different parameters or measurement methodologies and assumptions? Is there anything to account for uncertainty in the outputs? Dan alluded to the potential, particularly with different fluxes, could be both CO2 and non-CO2 gases. So do the models count for that at all? To what extent does the model incorporate socioeconomic drivers like market demand, land use change, and how does that incorporate into carbon stocks and fluxes? Does the model account for other potential impacts outside of the geographic area of interest? So Dan alluded to the sort of import and export of carbon. And the idea that could be touched through leakage. Also, what sort of software and licenses and computer resources do you need to run the model? Do you need an expensive license and a supercomputer, or is this something that you can run on your desktop? And that all leads to really ultimately what level of skills and resources are required to do the type of modeling. And do you have those capabilities in-house, or do you need to maybe potentially outsource some of that? And so what we've done as part of this, our sort of assessment framework, is that for these 15 different models, which I'll touch upon, is we came up with these key components of these models, and we've sort of come up with a very sort of tabulated, formulated way to try to account for all these different things you might want to think of. So this table itself, I'm not going to go into it at all, but it's just how you might be able to track these different components that I talked about, looking at it with using Landis 2 for the example, which is one of the landscape level mechanistic models that Dan talked about in one of his examples. And again, you can access all this information in the report. So we then said, well, if we've done this for 15 different models, this is a lot of qualitative information that still might be hard to sort of for people to synthesize and try to pare down sort of where are you know, what model is right for them and the type of questions that they're asking. So we also came up with sort of a sort of more defined set of model criteria and scoring rubric. And so with that, we had 15 different criteria divided into 3 sub-criteria based on usability, complexity, and analytical capability. And within each of those components, we had sort of a ranking of 0 to 10, about with 0 being has no capability to actually meet that criterion, like it's not included in the model, to 10 to have very high capability or sort of full extent or coverage. We use that then to come up with a score for an aggregate sort of between 0 to 10. And we did that for 15 different models that are sort of outlined on the right, of which sort of all sort of encapsulate one or more of the sort of modeling types that Dan talked about when he went over the review of the different approaches that can be taken. And so just to elaborate on the selection criteria, you can see things when it comes into usability, sort of how accessible is it in terms of open source, or does it require softwares and licenses? What's the learning curve to actually use this? You know, what data requirements are needed, particularly in terms of stuff that is required by the user, not that's just readily available by the sort of the model developer. On the complexity side of things, it's things like spatial resolution and extent, as well as temporal resolution extent. What type of silvicultural systems are supported? Can you actually tick boxes that say do a thinning from above, thinning from below, or do you need to actually parameterize all these, or does it even have the capability to cover specific silvicultural approaches, or does it have some other way to respond to management? What carbon pools does it track? And does it account for timber harvest at all, or is this more about just sort of ecosystem sort of growth and dynamics there? Does it track harvested wood products, and what pools does it track? And then on the analytics side, you know, are you able to do scenario analysis? Can you count for socioeconomic drivers or other sort of natural drivers such as climate sensitivity, fire, pest, and disease, right? You can think of ideally you'd want one that covers all of those, right? But is easy to run, has very high spatial resolution, and has all the data you need without having to formulate any of that yourself, right? But we know that in this world, right, that doesn't exist. It's not possible to get basically every single thing in a single model. And so what we can do is then take those criteria and we can put them together in this sort of scoring example, where here we've looked at Landis 2 and FBS, which is 2 of the higher scoring models in sort of our criteria, and looking at ways that we can rank the 2, right? So both are mostly highly accessible. They have sort of free licensing. They have about a medium learning curve, again, to get it up and running. Different levels of data requirements, sort of different levels of spatial resolution and extent. Both have good temporal resolution and extent. But where they differ most is that sort of Landis itself doesn't really have any economic drivers, whereas you can sort of account for some in FBS. But at the opposite end, climate sensitivity can be easily incorporated into Landis 2, whereas it's harder to do that in FBS. So you can sort of see different ways to look at it there. The other way too is that Landis by design is more of a landscape level model. FBS is more of an individual tree or stand level model. So a lot of this also can sort of differ based on sort of what are you really trying to model, how big is the scale. So we can go through that for all the 15 models and sort of come up with this sort of set of usability, complexity, and analytical capability scores, right? To come up with sort of total scores where I'm sort of ranked here based on sort of expert criteria, largely informed by myself and colleagues at the University of Maine, with input from others at the Forest Service, et cetera. But the key here is that there's no perfect model. Generally, again, the way that we sort of structure the different scoring, we found that growth in yield models and carbon calculators or some of these more bookkeeping type approaches typically scored higher, largely because they're a lot easier to use, and maybe some more of the data was sort of available off the shelf or easily accessible that could be sort of integrated into those systems. There's really a pretty clear trade-off between analytical capability and usability. The more analytical capability you want, the more coverage, the more extent, the more scenarios you want to run, the more impacts you want to account for, right? The more sort of the harder they are to either learn or use, right? So there is a trade-off there. And the other big component is really the data requirements that you as a user might have to provide, as well as the sort of licenses that you might need to purchase or access. And those can also decrease the usability as well. So the other thing I just want to touch upon as we sort of wrap this up is that a lot of these models, they sort of have one or several components of capturing the whole system, but rarely is there a model that can adequately capture every single sort of part of the system that Dan introduced when he went over the different aspects of a carbon budget, right? We talked about these growth and yield models. They're really good at building yield curves, right? But then you sort of need those yield curves if you're looking at more at something like a regional or state level assessment. You need to somehow come up with a way to basically build that into a landscape level simulation where you have sort of broader disturbance regimes, can cover succession, things like that, right? And then how do you report that out when you're dealing with aspects of sort of aggregate harvest and sort of timber demand needs, planning and policy support, which is often done at a sort of higher level, not necessarily stand by stand, particularly if you're looking at it from a sort of state agency or federal agency perspective, and accounting for these harvested wood products. Use that can then inform sort of other scenarios that might modify management regimes to sort of achieve whatever sort of your overall outcomes may be. And so you can think about then really what a way that you could try to approach that is like combine FBS or stuff from CBM, CFS into sort of more of these landscape level models, then produce sort of different estimates under different scenarios, and then ultimately look at how those scenarios, how those estimates could vary under different scenarios, which then could tell you information on things like terrestrial carbon, sequestration and storage, harvested wood products, market impact, et cetera. And an example of where we've done this is that we have it sort of integrated here in Maine. We've integrated Landis 2 with an economic optimization model to look at evaluating carbon and market impacts under 9 different sort of explicit silvicultural practices. And this was sort of demonstrated in our Forest Carbon for Commercial Landowners project and report that was released in March of 2023, where through this assessment, we found that you can increase carbon sequestration up to 20% without reducing total harvest, largely through changing management to a sort of more uneven age management type approach, right? And there's a bunch of alternative scenarios that we could do to sort of look at what if there were different drivers that affected that, you know, does that 20% number hold up? And we found it does under a sort of wide range of assumptions and uncertainties. I recognize it's hard for me to come in as an economist who looks at both basically forest carbon modeling through more of an economics or integrated approach and not talk a lot about the economic side of the model. So sort of shameless plug for, you want to know more about sort of what we went into that went to that previous study, you can go back to the November 2nd, 22 webinar by my colleagues, Aaron Weiskettel and Aaron Simons-Lagarde, that sort of talked about what went into that. And then also next month, this webinar is going to feature efforts to quantify potential leakage in forest carbon offset markets using sort of economic models, be led by Greg Latta and Brent Sanjan. I think I've been invited to also mention a little bit about some of my work in that space as well. So there's more coverage on those sort of types of modeling efforts in each of those webinars. And so just to summarize, there's several model framework and methods to choose from that Dan touched upon. Building upon that, there's actually dozens of forest carbon models currently available for us to use that are sort of off the shelf to some degree. But the models vary really in terms of usability, complexity, and analytical capability. And the ultimate choice of what models we want to use is really going to depend on the time and resources and the questions that are being asked. So each model is going to have its strengths and weaknesses. And really, the questions that you're trying to ask and at the scale that you want to ask them over are really going to direct, I think, which models you might want to select. Really, because of the complexity, it may be advantageous to engage experts on development and application, particularly if you're trying to look at things beyond the sort of stand level. And the caveat is that our criteria is really based largely on expert input. Those who basically have worked with some of those specific models more than we have might have sort of different opinions or sort of scoring apply with that because of their knowledge and know-how affiliated with each of those models. And as a result, these scores and recommendations are really subject to revision with more info and experience as we get to use these models more and more, particularly when it comes to sort of state, regional, and national level sort of policy implementation and assessment. So with that, if you want to learn more, go to the report that I already provided a link to. The report really includes a lot of links to detailed model assessment tables that can give you a lot more overview on each of the 15 that we talked about, in addition to sort of our scoring criteria. It's set up that you can also sort of adjust those criteria on your own based on your own sort of knowledge and insight. And with that, we'll open up to the sort of last 5 to 10 minutes for any sort of questions. And if we're not able to answer the questions here, feel free to contact us. And Dan and I are happy to get back to you in a follow-up sort of email. All right, thank you.
Yeah, thank you so much for your presentations, Adam and Daniel. So now we're going to move to that Q&A portion. We have a couple minutes left. So just to jump right into it. So first question that we got was, are these models applicable to just the US and Canada, or can they be used in other places such as like Africa or Southeast Asia?
I was looking at that question, so I'll take a first stab at it. I'm not sure which, generally speaking, of course, there's models that are used all over globally in lots of different regions. There's probably different ones than maybe we mentioned here that you might want to consider in tropical ecosystems that are more specific to those. But certainly, if I'm looking at the list that's on the screen now, the terrestrial TEM6, the terrestrial ecosystem model, was used in the tropics. And so is CLM Fates is being developed there. Those are more what I'm familiar with process-based models. I did look up, and I can. Well, I don't know if I can do it in the chat, but if you search information on the Canadian carbon budget model, the CBM CFS3 that's on the list here, that's been used a lot for lots of different countries. And even state level assessments, because it's more of a bookkeeping model that is can be downloaded, and they have self-study training. So it's pretty usable and pretty straightforward to use. And so that's been used a lot in different countries for these kind of IPCC requirement type reporting. I looked at their list of applications, and it's mostly in obviously Canada and the US, as well as Scandinavian countries in Europe, but some in China, not listed in a whole lot of developing nations. And I think that's probably because even though it is one of the more simple, straightforward models, it does require a lot of inputs in terms of forest inventory type data, especially yield curves, growth and yield curves and things. So if that information isn't like readily available, you would either have to come up and make those yourself to input, or you might need to use a more simple model like one of the ones I mentioned with Mexico, where you do a little bit more of a basic land use and paint the numbers on a map of carbon densities. And so those are some of my thoughts there. But you some quick Google searching, you can see where some of these different models have been applied outside of the US and Canada, which, as Adam mentioned, we wrote this report specifically for the eastern US forests.
Yeah, and quickly, I'd probably say about 40% of these models have been used elsewhere or have the capability to be. Things like the global timber model are already parameterized for other regions, right? But the level of detail that you're going to get about Africa, say, is not going to be the same as the U.S. for the same reason that Dan talked about, just what inventory data is available that are used to parameterize these larger models. So great question.
So another question we have are, very briefly, what are some pros and cons between utilizing maybe a more traditional statistical approach versus a process-based or deterministic approach?
Me to take that? Yeah, I think that's the same. This answer there is the same lesson that Adam has been really talking about is really how much data that you have and what your sort of learning curve is going to be for these things. I would say for, if you need some kind of general reporting carbon type estimates of carbon at time 1 and time 2 for some general ecosystem pools, and that's what you need to report as far as a carbon project or an offset or looking at mitigation goals. It's probably best to try to use inventory data where they're available. And that's in developing nations for the most part that have kind of these stronger and regular inventory, national forest inventory programs like in Canada, US, Scandinavia, now in Europe and now in Mexico as well. The reason to get into the more complex the process-based modeling is if you have specific objectives to look at. I would say, especially if you're interested in how climate change, there's this issue of CO2 fertilization. That's something that's difficult to tease apart from inventory models that don't have a lot of attribution of these different things. You kind of know how much carbon is there one time and how much is there the next, but you don't really know how it got there or what's controlling it. And so that's where, if you want more detailed questions like that, you would work with process-based modeling. But the data requirements and the learning curves are going to be much higher for those. And in those cases, I'd recommend just reaching out to the modeling team themselves and see if they've already done a simulation or application that's similar to yours, and see if you can get information that way.
Yeah, and the only quick thing to add on that is that, again, when you're doing inventory-based assessments, you're really constrained on the statistical side with what's been performed on the landscape or in that plot or whatever, right? And so your ability to extrapolate, if say you want to explore alternative species that are being grown in a certain area, or the effect of various silvicultural treatments that maybe haven't been measured enough to have a certain statistical sort of feedback, then it might be hard to extrapolate sort of to these sort of newer areas that could evolve under a number of different sort of shocks or management changes.
Great, thank you so much. And I'd like to thank our speakers once again for both their time and information. Again, the webinar recording and slides will be posted within a few days to be included on our mailing list, and to receive registration details and information regarding upcoming webinars, please email forestc@msu.edu. And I hope all of you have a great afternoon.
Thanks, Chad. Thanks, everyone.
Thank you.
Yeah,